All right, everybody, good afternoon. Good to see everybody here. Let's get the lecture going for this afternoon. So, how is everybody doing? How was everybody's weekend? Did everybody have a good weekend? It was good? Some people good? Okay, just a bit of a serious point related to that. So in the first week or two of university, it's always very exciting. There's always a lot of energy. But do remember, so a semester, it's very much a marathon, not a sprint. So do make sure you take a bit of time at the weekends to, relax, recharge, and get ready for another week of physics. So today, the subject, as you can see, it's about scalars and vectors. Has anyone done scalars and vectors before? Okay, so some people have, some people haven't. Okay, so that's fine. So a scalar is any quantity which has what we call a magnitude, so some kind of value, but it doesn't have a direction. Whereas a vector is something which has some kind of magnitude, but it also has a direction, so it points in a specific direction. And we're going to be finding out a lot more about that today. Now, the lecture is about, I've called it scalars and vectors. But actually, all last week, all those things we were studying about last week, so all those values with units and standard form and significant digits, all those things we were learning about last week, they were all examples of scalars. So we've actually already done scalars. We just didn't call them scalars. We were just talking about, numbers and values, but they were all examples of scalars. So we've already really done half the lecture for today, and we just need to focus on vectors. So I do like to start with a picture that has a connection to what we're going to be learning about. And this week, I found an absolutely fantastic picture, and I think it really sums up all the concepts that we're going to be learning about today. Let's take a look. So it's this absolutely stunning picture of the sun from NASA's Solar Dynamic Observatory. Don't you think that's just an absolutely stunning picture? I think it's absolutely extraordinary. There's just so much physics going on in this picture. What's the first thing everybody thinks of when you think of the sun? Well, you think, okay, the sun, it's hot. And temperature is a classic example of a scalar quantity. So temperature has a value, it has a magnitude, so maybe your temperature is 1,000 degrees Kelvin or 10 million degrees Kelvin. But temperature doesn't have a direction. It doesn't point in one direction or another. So temperature, a classic example of a scalar quantity. Can you guys see those arcs and loops towards the edge of the sun? Can you guys see that? Yeah. Does anybody know what causes them, causes those features, all those arcs and loops? The solar flares, that's what we call them. Does anybody know what physical force causes these arcs? Yes? Gravity. So it is affected by the sun's gravity. It's actually a different force. Any thoughts? So it's actually caused by the magnetic field of the sun. So the sun has an extraordinarily powerful and convoluted magnetic field. And that magnetic field is essential to understanding what's going on in the sun. And it causes those extraordinarily large loops and features and all that dynamic stuff going on in the sun. And magnetism is a classic example of a vector quantity because a magnetic field has a magnitude and it also has a direction. So just in this one image, we have a couple of great examples of a scalar quantity, temperature, and a vector quantity, the magnetic field there. Just to give you guys a sense of scale, can everybody see that tiny, tiny dot in the corner there? Can you guys see that? So just for a sense of scale, to the same scale, that's the size of planet Earth there. So we're just a tiny speck there, much smaller than even some of the smallest of these arches there. Obviously, it's just a scale in terms of the size of the planets. Unfortunately, we're nowhere near that close to the Sun. Otherwise, that would be very bad news. So that's just a very brief overview of vectors and scalars. So let's take a look in detail at what's on the menu for today. So the main thing that we're going to learn about today is, in a sense, vector mathematics. So how to write vectors, how to calculate their magnitudes, and how to add vectors. And then before we get to that, I'm going to do a bit of a compare and contrast with some scalar quantities and some vector quantities. So we're going to look at distance and displacement, and speed and velocity. Before we get to that, I always like to start with a bit of a quick recap of some of the concepts that we've done last time. So that's the plan for today. I'll just mention, whenever I put up these plans for today, the things we're going to think about, they're always a bit of a kind of provisional plan, always subject to change. So we never know exactly what's going to happen. Maybe we're going to have a question up here which is really interesting. Maybe we want to take a bit more time to discuss that in a bit more detail. Maybe some of you guys are going to have some of your questions, some things that you guys want to ask. That's going to take up a bit more time. That's all absolutely fine. If we don't end up doing everything on the plan for today and we do some stuff next time, that's always absolutely fine. So let's get started with this quick recap question here. So the question is about measurement uncertainties. Let me just see if I can start the question here. Here we go. So very often in science, we want to take repeated measurements. We don't just want to take one measurement of one thing and one and done, and we move on. We like to take repeated measurements of the same thing because that's going to give us better results. So suppose we're taking repeated measurements of the same quantity and averaging them. Which of these is that going to help? Is that going to help our precision? Is that going to help our accuracy? Maybe it's going to help both. Maybe it's going to help neither. Let's see which one it is. Let's take a look at the results. Let's see how we're doing here. All right, so nobody's going for D. We're kind of pretty evenly split for B and C. Not so many people are thinking about A. So remember which was which. If we had all of those darts clustered together but skewed off from the bullseye, then that can be precise but not accurate. Whereas if we had those darts all kind of clustered around the bullseye, then we might say that that's precise but not especially accurate. So if we take lots of repeated measurements, that's going to help improve our accuracy there. So very well done, everybody who got that one, C, the correct answer. So just remember, if our measurements are imprecise, so maybe we have some systematic offset that's putting us away from the bullseye, we can take lots of those measurements, lots of those repeated measurements, and average them. But that average is still going to be that offset from the bullseye there. So repeated measurements, they're not going to help with our precision there. So very well done, everybody who got accuracy there, because this was quite a tricky question, had to think a bit about it. So very well done, everybody who got that one. Let's try another recap question, thinking a bit more about units. Let's try this one here. So suppose we had a meter cubed of water. How much is that cubic meter going to weigh? So again, if you're not sure, this kind of question, it's very handy to draw a diagram of the situation. So sketch out everything that's going on. That can really help to work it out. Let's take a look at the results here. What do we have? All right, so not so many people going for C, but we got it seems pretty egalitarian here. We've kind of covered all the bases, so we're going to have something right here. Now, this is a bit of a tricky one because I can understand why you might say, well, we've got 10 centimeters, so we could fit 10 of them into a meter. So maybe our cubic metre of water is going to weigh 10 kilograms. So I can see why you might be going for 10. This is why it's really handy to draw a sketch of the situation. Let's imagine we were laying out some cubes on the ground here. So we'd have 10 by 10. That's going to give us 1 metre squared of water. So we'd have 100 kilograms. And then we can stack 10 of those on top of each other. So we're going to have 10 times 100 kilograms to give us our metre cubed of water. So the correct answer is that our metre cubed of water, it's going to weigh 1,000 kilograms. So again, it's a tricky one. So very well done to the people who got that one right, because it is a tricky one. So if you're not sure about this, don't worry at all, because we can have plenty more practice in the workshop with these kind of questions. But it does really help. If you're not sure, always draw a diagram, have a sketch of what's going on, have a chat with the people around you. And you can always ask if you're not sure and you want a bit of help. But very well done to everybody who gave that question a go. Does anybody have any questions about either of those two before we move on? So before we move on to scalars and vectors, I'd just like to share with you guys one more thing about units. And this thing, it's my own personal secret top best pro tip about units. And it's a bit of a kind of secret top tip about units, but it works fantastically well. So I'd just like to share it with you guys before we move on. So in a nutshell, my single best top tip about units, it's that units, they're not the cherry on the cake. So what do I mean by this? Let's imagine you've baked a delicious cupcake like we've got up there. You've baked the delicious cupcake, and someone's going to come along and they're going to try the cupcake. They're just about to try the cupcake, and you say, no, wait, the cupcake, it's not finished yet. Let me throw some cherries on the cake, and now the cake's finished. Now you can have the cake. We often think about units in much the same way as just the cherry on the cake. So maybe we've got some physics question, maybe we're calculating the velocity of something. We work out all those numbers, all those digits that we like so much, and we get some velocity there. So velocity is 8.94. Oh, fantastic. And we're just about to hand in our work, get the marks, and then we say, stop and wait. Let me throw some units on that for you. So it's a velocity, so the units, it's going to be meters per second. Now the question is finished. So I call this approach thinking about units as the cherry on the cake. And I'd really like to encourage all of you, don't think about units as just the cherry on the cake, as the thing when you finished your question. If we think about units a bit more intrinsically, units can actually help us to check our work. They can help us to check if what we've done is correct, and they can help us to solve new problems. The way we do this, this is my top secret best pro tip about units here. If you only write down one thing in your notes from this lecture to take away about units, this is it. The secret is you need to treat units like any other part of the equation. That's the secret tip. That might sound a bit unspecific, so let me show you a couple of examples of what I mean by this. Let's suppose we had an algebra question. Let's suppose we had an algebra question and we're trying to solve for x. So we've got this question up here, and we're just trying to solve for x as an algebra problem. Before we go on, I'll just say I always avoid trying to put algebra up on the projector screen, because nobody can take an algebra in PowerPoint form. Everybody's eyes just glaze over. No one can take an algebra on the screen. So I'd just like to say I'm really just putting the algebra up on the screen really for sort of illustrative, really for decorative purposes, just to make the point. So please don't worry too much about following along the details of the algebra. I'm just putting it up there to make a point. If you want to view it as more like wallpaper, that's absolutely fine. That's really the sense in which it's intended. Let's suppose we had this algebra question. Here's what nobody does when they're solving an algebra question. Nobody does this, and I really want to emphasize, please don't do this when you're solving algebra questions. Nobody does this. Step one, forget about A and B. All those A's and B's, just forget about them. Just think about X and the numbers. Those coefficients A and B, we're just not worried about them. Take them out of there. And then you work out the numbers part. We work out the numbers. What do we get here? And then we get X equals some value. And then the last step at the end, put A and B back in when we're finished. So we get X is 11, A, B. So when it comes to algebra, nobody does that, right? Everybody knows that's not how you do algebra. So what do we do when we're doing algebra? We keep the A and B in the equation. So, we do all that algebra stuff. You rearrange the equation, and you simplify it. You move the terms around, and then you solve for X, and we get X is 11, A over B. And we don't have to put the A and B back at the end. They're just there at the end when we're finished. And if we compare these two, we can see we've got A over B over here and AB over here. So they're very different. And we wouldn't have known that it was supposed to be A over B if we just did this business of putting the A and B back at the end. When it comes to algebra, that just seems totally straightforward. Nobody would say that this don't do this column is a good idea, and everybody gets, yeah, sure, that's just how you do algebra. But when it comes to physics and to units, people seem to think a bit differently about this. So let's take a look at exactly the same situation, but just with a physics concept. Suppose instead of solving for X, we're solving for V. Maybe we're solving for a velocity. And instead of A and B, we've got meters and seconds. We're actually going to see equations like this in a few weeks' time. But for now, let's just think of it as an equation with meters and seconds in. So when it comes to physics equations, people are much more keen to say, well, we've got meters and seconds in, but let's just forget about them. Let's just not bother with the meters and seconds. Let's just, work out the numbers part, and then, do the calculations. We get V. And then at the end, we'll just put the meters and seconds back in. So even though nobody does this when it comes to algebra, when it comes to physics questions, people seem to think, oh, that's kind of the way to go. So my top secret best tip for dealing with units in physics is to treat them like any other part of an equation as you would in algebra. So suppose starting back up from the top, what we want to do, rearrange, but we keep the meters and the seconds as part of the equation, just as we did with A and B. Then we simplify, then we're nearly there, and then we solve for V, and we get V is 11 meters per second, which is the correct units that you would expect for a velocity. But whereas with this one, we have to just put the units back in at the end and kind of hope that we get them right. If we go over to this side, the units just come out of the equation. We don't have to put anything in artificially by hand. So that's already something that's important. The reason that this is such a good way to deal with units is because it allows us to check if everything has gone correct. If we're expecting the units to be meters per second, we should hope that's what they come out as when we get to the end. And if they don't, we know we've probably made a mistake with our algebra. So by keeping the units in your equation, by treating them like any other algebraic part of the equation, it makes our life much easier. It tells us what the unit's going to be at the end, and it allows us to check our work as we go along. So I know it can be tempting to just say, well, we'll just ignore the units and worry about the numbers and put the units back in at the end. But I really encourage everybody, treat the units just like any other part of the equation. It's a much better way of approaching units. Does anybody have any questions about that? All right, so I think let's move on. Let's start thinking a little bit more about scalars and vectors. So I think we've got another question coming up here. Suppose we've got some momentum. Let's think, what are the units of momentum? Let me just get the question started here. So remember that momentum, it's mass times velocity. So we don't have to guess what the units of momentum are going to be because we know what goes in, so we know what has to come out. Just a quick tip about the notation here. So you can see we've got those square braces here. So these square brackets, if I put something in square brackets, it means the units of that thing. So usually you might say momentum is equal to mass times velocity. But if we put them in square braces like this, it means the units of whatever's inside it. So what are the units of momentum there? So if you're not sure, think about, well, what are the units of velocity? And then we just need to add in the units for mass. And then we're there for momentum. All right, let's take a look at the results here. What do we get? All right. OK, so remember that the units for velocity are meters per second. So the units for velocity are meters per second. And remember, we can write that as meters per second this way. So those are the units of velocity, meters per second. And then momentum, it's velocity times mass. So we just need to add that, to multiply that by kilograms. And we get option C here. So the units for momentum, it's kilograms, meters per second. So very well done, everybody who got that one and everybody who gave that one a go. That's really good thinking there. Does anybody have any questions about that before we move on? All right. Now, velocity and momentum are both classic examples of vectors because they both have a magnitude, so how much of the thing, and they both have a direction. So we might say, well, you've got a velocity or momentum in a particular direction. So let's do a bit of a compare and contrast of some scalar and vector quantities and have a look at the difference here. So I think the story of scalars and vectors as a comparison, it really starts with distance and the equivalent vector analogy of that, which is what we call displacement. Let's take a look. So we've got distance and displacement. Distance is a scalar quantity. It doesn't have a direction. What does this look like? Suppose we've got 2 points and we think about the total path traveled. That's going to be our distance. So we've got 2 points here and we go on our little journey between 2 points and maybe we can go all kinds of ways. Maybe there's a forest or some mountains or something that we've got to go around. So this path here is our distance. And there's no particular direction associated with that. It's just how far we've traveled. So at some point in our journey, maybe we're going one way, and then another point we kind of turn around and go the other way. There's no one specific direction associated with this. So we say the distance, that's a scalar quantity. The SI units for distance, it's meters. Of course, we can measure distance in any units we like. So maybe you're more familiar with measuring distance in miles. It's still a scalar quantity. The vector equivalent, if you like, of distance, we call it displacement. Now, displacement is a kind of no-nonsense kind of thing. It's just the direct path from where we start to where we finish. So it's just the directs between our start and end points. Look something like this. So no nonsense, no messing about, no detours. It doesn't take the scenic route. It doesn't stop to take a look at anything on the way. Our displacement is just that straight path between our start and end points. Displacement has a magnitude, so how long that arrow is, and it also has a direction, so whatever direction that displacement is pointing in. So whereas distance, it has units, it doesn't have a particular direction, so it's a scalar quantity. Displacement has units, the units are actually the same. It also has a direction, so displacement is a vector quantity. Once we have distance and displacement, we can then talk about the related concepts of speed and velocity. So speed is our distance divided by time, divided by how long it took. And we say speed, it's a scalar quantity. So maybe your speed is 20 meters per second, but there might not necessarily be a particular direction associated with it. Whereas velocity, it's our displacement divided by time. So just as the displacement, it comes with some direction built into it. If we then say, well, how long did that displacement take? That gives us our velocity. That velocity, it's going to have the same direction associated with it. So velocity, it's a scalar quantity. So that's the basic idea with a few examples. But you might think, well, okay, we've already covered how to write down units of things. But if we're saying, well, velocity and displacement, they have directions, how do we actually go about dealing with that when we're working with these concepts? Maybe we've got some questions here, maybe we're working through something in the workshop. How do we actually deal with the fact that something has a direction? There's a couple of different ways, so let's take a look. So when it comes to vector notation, there's a few different ways that we can write the same vector. The simplest way is we can just write the magnitude of the vector with some direction. So I've got some examples here. So maybe we have a force, and it's some particular value of newtons, and then we can just write the direction. Maybe the force is up. That's a perfectly fine way to write down a vector. Or maybe we have a displacement vector there, 3.1 centimeters east. So we're just writing down what the direction of that vector is. So we have the magnitude, 3.1 centimeters, and the direction, east. Absolutely fine way to write a vector. Things get a bit more interesting when the direction isn't just straight, up or down or east or west. Sometimes our vector can be at a particular angle, so maybe we have some velocity, maybe that could be 37 degrees above the horizon. That's an absolutely fine way to write a vector. Let's see what these vectors look like when we sketch them out. So that force going up there, you've just got the force. So the magnitude of the force, that corresponds to how long the arrow is, and the direction just corresponds to whatever the angle is. So that's what our force might look like. What might that x, that displacement vector, look like? Well, it's 3 centimeters to the east, so maybe it might look something like that. The most interesting vector here, it's this one, so this velocity, so 5 meters per second, 37 degrees. That might look something like this. So we've got 37 degrees there, and then we have our vector. It's a bit more interesting because it's not in any particular direction. And we can talk about this vector in terms of what we call vector components. So we have the magnitude of this vector, which is 5 meters per second, and we have the angle there, 37 degrees. But we can also talk about this vector in terms of the pieces that it's made of. So we might say it's got a horizontal component that we call V1 and a vertical component that we call V2. these components are actually a very useful way to write down vectors. So whereas here we have a magnitude and direction, we can write out the exact same vectors, but instead of a magnitude and direction, we can write the vectors in terms of their components. It's probably easiest if I just show you some examples and you can see what I mean here. So suppose we've got this force, 4.54 newtons up. In component form, that vector might look like this. So for that force, we've got 4.54 newtons up. And we might say that that first component, maybe that's the vertical component of our vector. And maybe that second component, maybe that's the horizontal component of our vector. So our vector is only up. So it only has the vertical component. There's no horizontal component. If we look at this displacement vector here, so 3.1 centimeters east, so maybe the components of our vector are how much north and south our vector is and how much east and west. Well, our vector over here, it doesn't have any north or south component, so that component over there is just 0. And then we're going 3.1 centimeters east. So the components of that vector, that's what that looks like. Writing vectors in components really becomes handy when we have vectors like this last one, where they're not just in a particular direction. So instead of writing 5 meters per second at an angle, we can just write down the components. So maybe the horizontal component is 4 meters per second, and the vertical component is 3 meters per second. Something that's very important to emphasize is even though these two might look different, they're exactly equivalent ways of writing the same vector. And it's very important to be comfortable with seeing both of these different ways of writing vectors as different ways of writing the same thing. We're going to have lots of practice in the workshop of converting between writing vectors in one way or another. And it's really important to get the practice in and just get the experience with working with vectors like that. So that's the basic way that we might be writing vectors. But sometimes when it comes to vectors, we're not interested in the direction. We only want to know what how long it is. We only want to know what the vector magnitude is. So how do we go about that? Suppose we've got this vector here. Let's think about that. Suppose we don't mind what the components are or what the angle is. We just want to know how long the vector is. We call that the vector magnitude, and we write that with some square lines like this. So if we have a vector and we say we just want to know the magnitude, then we put the vector in some square lines. And that just means the magnitude, so without the direction. And we can calculate that with Pythagoras' theorem. So we can think of the magnitude of the vector and the components as forming a right triangle. And then we can calculate the magnitude of the vector just with Pythagoras' theorem, thinking about the components of the vector. The last thing we have to think about vectors for today is how do we add vectors together? How do we go about this? Maybe we've got one displacement vector and another displacement vector. How do we work out what our total displacement vector is? Let's have a look at this. The way we do this is we add the components of the vectors together. Let's really spell this out. Suppose we've got vector A over here. It's got some magnitude and direction, and it has components A1 and A2. You can probably guess what's coming next is vector B, and we can represent adding these vectors by drawing them one vector after the other. Now vector B, it's got components B1 and B2. So these are our two vectors that we want to combine. We could write these vectors down mathematically with components there. So maybe vector A, it's got component A1 and A2. Vector B, got components B1 and B2. Maybe we might say when we add them together, that's going to be vector C. So graphically, vector C is going to look something like this. And it's going to have components C1 and C2. This is one example where maybe the diagram starts to look a bit confusing, but it's actually more straightforward if we look at the equation. Because as an equation, it's quite straightforward. We just need to add the components here. So vector A plus B, we can work out the components just by adding the components of A and B for part 1 and for part 2 there. And that's going to give us the new vector. Let's try a quick question about vector magnitude here. So suppose we have a couple of displacement vectors. So maybe you might drive 1.4 miles north, and then maybe you drive 1.3 miles west. And we want to know, well, what's our displacement vector? How far are we from where we started? So we can do this by working out the magnitude of these two vectors. So let's start this question up. For this question, we're going to need to add the vectors together, and then we're going to need to work out the magnitude of what we end up with. So you can see the hint there. It's very helpful to draw a sketch of this. So start by drawing a sketch of that 1.4 miles north vector, and then add the 3.2 miles west vector. Just draw a sketch of what the resultant vector is going to look like, and then we can think about working out the magnitude. So I'll give you guys a bit of time to work that one out, and then we'll see what we get. All right, let's see what we've got here. Let's see what we've got for our results here. All right, so nobody's going for D. Looks like most people are going for B. How many of you tried a sketch of the diagram? How many of you drew the... Was it helpful? It's always a good tip with problem solving. So very good. Looks like most people got that one, 3.5 miles. That's fantastic. Very well done, everybody. Seriously, that's really good, because we had to add the vectors. We had to get the magnitude. That's all new stuff, okay? So very well done, everybody. That's really great. That's really good. Okay, so just in the last few minutes of the lecture, I'd like to just think about a bit more of the bigger picture for a moment here. Let's try a different question for you guys. So we're thinking a bit more outside the box here. What I'd like to ask you guys, which of these 4 skills would you say is the most important skill for a scientist? So these are all important things that scientists might want to do. Which of these would you think is the most important? Oh, they're already coming in. It doesn't usually show this, but this is adding a bit more of the drama to it. Oh, this is quite exciting. I don't usually see the results coming in live. Where's it going to end up? It looks like we have a clear winner out ahead. So it really looks like a kind of race for second place at this stage here. How are we doing here? I think we've nearly got all the results in. Okay, so I think it looks like we do have a clear winner here. Okay, it does look like most people are going for A. Maybe we'll have a few more going in, but it looks like then we're pretty evenly split between B, C, and D. So thank you all, everybody who put an answer in that. I'm very curious to see that most people think asking questions, because I would 100% agree with that. So all of these fine other things, they're all important skills for scientists. But if you ask me, I'd say the single most important skill for a scientist really is asking questions, because science really starts when you ask questions. So I'd just like to wrap things up for today with just one slide all about asking questions. So thank you all for putting your answer in, and I'm pleased to think that you'll go in for that answering questions there. let's start with this picture here of the apple tree. So, of course, this apple tree, it's very famous for physics because the story goes Isaac Newton, he was sitting underneath the apple tree, and the apple falls on his head, and he invents the theory of gravity. Now, that story, maybe it was embellished a bit, maybe it didn't actually happen. I don't think that really matters. The important point is that Isaac Newton was one of the first people to actually ask, well, why does the apple fall to the ground? Now, you might say, well, that's a bit of an obvious question. It's because of gravity. But until it's asked, it's not obvious at all. And you might easily say, well, Isaac, why are you asking such silly questions? Of course, stuff just falls. That's just what stuff does. When an apple comes off a tree, it's just going to fall. Stuff just falls. That's just how the world works. It's not going to come off the tree and go up or just hover. That would be weird. It's going to fall down. So it really does take a lot of creativity to ask something like, well, why does it fall? And that skill is really essential to becoming a scientist. There's a few points I'd like to make about this. So it really is an essential skill for becoming a scientist. We often focus on the more technical, the more mechanical side of things like crunching the numbers and writing the code and doing the experiments. But it really does start with asking the question. When it comes to skills, we often more think of things like maybe playing the guitar or gymnastics or playing golf or boxing. We always think, okay, that's definitely a skill. And we often don't think of asking questions as an intrinsic skill in itself. But it really is a skill. And like any skill, it improves with practice. So the more you ask questions, the better you get at asking them. The other advantage of asking questions is you can help other students. So if we're halfway through a lecture and I'm talking about something and it doesn't make sense and you have a question about it, probably most of the other students who are in the lecture are also thinking a similar kind of question. And you can really help the other students by asking that question. And they're probably going to be really glad that you did. So I'd really encourage you, if you do have a question during the lecture, please do make sure you ask it. It can be difficult to ask smart questions. Maybe there's some really technical thing and you want to get to the heart of the issue, but it can be difficult to start off by asking a kind of really smart question. So what I'd encourage you all is, please don't worry about that. A great place to start with asking a question is just, can you explain it differently? It doesn't have to be a really smart question, you know, what's the derivative of x with respect to... Don't worry about any of that. Just start by asking something. We can get the dialogue going and we can figure it out. The important thing with asking questions is just to start. The last thing I'd like to say to wrap this lecture up is to leave you guys with a challenge. So my challenge for you guys is to write down one question from every lecture that you go to. Not just for this physics module, not just for your foundation year, but every lecture that you're going to go to for your whole degree. Maybe to start with, it's going to be tricky to come up with a question. But as you practice, it's going to become more and more natural, more and more straightforward. Maybe the question's going to be obvious. Maybe there was something in the lecture that wasn't clear or that didn't make sense. Well, you can ask about that. But it doesn't have to be a question just about something that you don't understand. Maybe you've seen something similar in a different module and you can say, well, how does this relate to that? Or maybe you've read about something or there's some different idea. You can say, well, how does what we're learning here relate to that? So my challenge for you is every lecture you go to, get in the habit of just writing down one question. And that's really going to help when it comes to asking questions. And we can certainly ask about them in the office hours or the drop-in help sessions or the workshops, or please do always feel free to just ask during lectures. So I think after all that, I think I must ask, are there any questions about any of this, about asking questions or about vectors? If you don't want to ask now, we have the drop-in workshop immediately afterwards. We can go through the questions then. maybe we can have a chat in the drop-in help session if there are any questions. But that's all I wanted to say about vectors and scalars for today. So the next lecture is on Thursday. We're going to be starting on forces. So it's a really exciting topic, really getting into some great physics then. So I hope everybody has a great week. Thank you all for listening, and I'll see you next time.